So yesterday when we were talking about simple harmonic motion, we looked at a mass on a spring and we looked at a pendulum. But yesterday we only looked at that from the perspective of what things can affect the period of those oscillating objects. Right? Today we're going to look at them from an energy perspective. Right? We're going to spend more time looking at a mass on a spring because mass on a spring involves elastic potential energy. Okay? We don't need to spend a lot of time looking at the pendulum in terms of law of conservation of energy because a pendulum has what kind of potential energy? Gravitational. We've already done problems in Unit 2 that involve the conservation of mechanical energy using gravitational potential. So today will be heavily focused on masses on springs because we haven't talked about the elastic nature of springs and other elastic objects until today. Okay, so what we're going to look at is first Hooke's law, because Hooke's law is kind of the basis or the foundation of elastic potential energy. We're going to look at that from the perspective of, first off, his law, and then secondly, the work lab you did in Science 10, and then how that relates to energy in a spring. All right, so we're going to understand the relationship between restoring force, F, okay, and spring constants, which we learned yesterday is abbreviated with K, and displacement. Here's the weird thing, guys. In this unit, displacement is represented with X, not D with the arrow over top. The reason for that is this. In this unit, displacement is always measured from equilibrium. It's not measured from point A to point B. It's always measured from equilibrium. So we use X for that. Okay, everyone with me on that? So rather than saying, over the course of an entire trip, my displacement is this, it's just how far from equilibrium are you? Are you ahead of it or behind it? Okay, so it's still a vector quantity, okay, but it just works a little different. So we'll use X for displacement in here. Okay, we're going to look at how energy is conserved in simple harmonic motion. Obviously, it's conserved in all things, but this day in particular, simple harmonic motion. Okay, and obviously that potential energy in simple harmonic motion can be elastic as well as gravitational. Okay, but from the mass on a spring perspective, obviously it's elastic. Okay. So Hooke did a lot of studying with springs, and he discovered some what would now be considered very simple things, okay, about springs and other elastic objects. Okay, what he found was that elastic objects pull back with an equal amount of force to however much they're being pulled on. Okay, which that's kind of Newton's third law, but it kind of makes sense for a spring. Okay. But what he also discovered was that the more you pulled on something, the further it would stretch. Again, that's not rocket science, but the relationship he found was that it is linear. If I double the amount of force I pull on a spring with, I will double the length of the spring. Okay, or I'll double how far it stretches. Maybe not double the length of the spring, but I'll double how far it stretches. All right, so he discovered, okay, that this relationship was true. He discovered that very simply by hanging a spring from the roof and then putting ever increasing mass on the end of it. Okay, so what force was working against the spring? Yeah, force of gravity. So really, his experiments were just saying that the force in the spring, which we know as the restoring force, trying to bring the spring back to equilibrium, was equal to the force of gravity. Okay, so he was able to calculate in newtons how much force he was putting on the spring simply by going m times g. Okay, now, how did he know that the spring was exerting the same amount of force back? Think back to Unit 2. Okay, this thing isn't oscillating. He just hung the mass and hung there. It wasn't moving. Okay, there was no acceleration, therefore the net force was 0, and the force in the spring was balancing the force of gravity. All right, so that's why he did it this way. So what he measured was the displacement of the spring. So he knew how long the spring was when it wasn't stretched, and then he measured how far it stretched each time that it was that essentially he put more mass on. And what he discovered was X was related to some quantity about the spring. Okay, the spring constant of the spring. The heavier the spring he used, the less it would stretch. Okay? So he discovered then that the force in the spring was the spring constant times the displacement of the spring. Okay, now why do I have this negative on here? I have gravity on one side, but I have a negative on my spring force. It's pulling up. The spring always pulls in the opposite direction that it's displaced. That's why the negative sign has to be there. Okay? If I pull a spring to the left, the spring pulls to the right. Okay? So my displacement would be left. But I don't want my force to end up left because I know the spring is pulling the opposite way. So I always have a negative in my Hooke's law calculations to ensure that the vector I get on this force is opposite the displacement of the spring or elastic object, whatever it happens to be. Okay, everybody all right with that? Hooke's law is not difficult to use. It's a 3-variable formula. Okay, everything in it is multiplied. Okay, so it's pretty simple to manipulate, pretty simple to use. Okay, everybody all right with Hooke's law? Negative k times x. Spring constant times the displacement with a negative in there gives us the proper magnitude and direction of the restoring force in the spring. Okay, so that's Hooke's law, right? Unfortunately, probably a less famous discovery than discovering cells. Which is unfortunate because this is physics and it is more important, but whatever. Okay, all right. So stated mathematically, like we said, Hooke's law is negative k times x. The negative sign is used to ensure that the force is always directed opposite. Now, from an energy perspective, how do I calculate the energy that would be, or the work I would do in stretching the spring? Force times distance, right? Work is always force times distance. Okay, that's how I would calculate the work I do in stretching the spring. When you did this in Science 10, you did it not with a spring. Well, actually, you did. The spring scale has a spring in it, obviously. Okay, but you did it with a rubber band. Okay, so you got a graph of force and distance. That's supposed to be a D. Okay, that looked like this. Okay. Now, when you did this lab, you were asked to calculate the area underneath this line. What did that calculate? No, displacement's already here. Displacement's on the x-axis. If I calculate the area underneath this line, I'm taking the force, right? I'm going base, the distance, times the force divided by 2. So essentially like the average force. Okay, so I calculate the area underneath. I'm going force times distance, which gives me work. All right, but I'm only using half of the force. Agreed? Because it's a triangle. Okay, so when I did that, okay, essentially then we had this. Distance times force over 2. Okay, now, what force was I working against? When I pulled on the elastic band, I pulled toward me. The rubber band pulled the other way. Would that be governed by Hooke's law? Right? I was working against the restoring force of the rubber band. Okay, so if I'm working against the restoring force of the rubber band, what formula calculates this? Negative k times x. All right, but we said I only want to use half of that force, right? Because it was a triangle. So I've got 1/2 k times x. So there's my force times my displacement to get the energy, right? Is that times x again? Right, because when we do this for simple harmonic motion, we use x instead of d. So what's x times x? Okay. There's your formula for calculating elastic potential energy. Okay, this is why we actually have you do the work lab in Science 10. So we can go back to this and say, hey, when you did this, you were working against a restoring force. You took the average restoring force, multiplied it by the distance. You didn't know it's what you were doing then. You thought you were just calculating work. But that work was the elastic potential energy stored in the rubber band. Okay, that's where we get that formula from. We derive it in that way. Okay, so what Hooke's law is saying is that The further you pull something, the harder you have to pull, okay? But from an energy perspective, that makes a linear graph, that makes a triangle, okay? So we have to go 1/2 times the force times the distance, and we get our elastic potential energy. Okay. So that's kind of what we're looking at here. Okay, so we just looked at how we derive that formula. That is true for any elastic object. It's true for a spring, it's true for a rubber band, it's true for a bow and arrow. Okay, now how do I measure distance in the bow and arrow? I measure how far the string comes back. So here would be the resting point of the string, okay? I would measure that distance there, okay? That would give me, okay, the distance over which I pulled or did the work, okay? It would also be equal to the distance I pull the two ends of the bow together, okay? Because really that's what you're doing. When you load a bow, okay, you're pulling the top and bottom together. It's the bow that has all the potential energy, not the string, okay? It's the bow that wants to snap back to straight. Okay, everybody all right with that? Now, here's the other thing we need to realize. At equilibrium, how much potential energy is there? 0, because what's x at equilibrium? 0. Okay, so that's why when the object is oscillating back and forth, okay, here and here, the maximum stretch and the maximum compression, okay, those are points where we have lots and lots of potential energy. In fact, all of the energy is potential. But when we're moving through equilibrium, all of the energy will be kinetic, right? And at a point maybe halfway in between, some would be kinetic and some would be potential. All right, so the same thing is going to govern this as governed a roller coaster. We're still going to say that the initial mechanical energy equals the final mechanical energy. It's just instead of going m times g times h, now we're going to put in 1/2 kx squared. So we'll still say this, initial potential plus initial kinetic equals final potential plus final kinetic. That's all still true. Okay, it's just now this isn't gravitational. So now it looks like this, 1/2 kxi squared plus 1/2 mvi squared equals 1/2 kxf squared plus 1/2 mvf squared. Right? There aren't different kinds of kinetic energy. Either you're moving or you're not. Okay, but there are different kinds of potential energy. Now, what's in every single one of these terms? The 1/2. So when you're manipulating this, can you get rid of it? You can. Okay, as long as you're not trying to solve for a form of energy. If you're trying to solve for an x or an f, you can cancel the 1/2. If it asks you what's the potential energy, you have to leave the half in there. Okay. All right. So does this look like something we'll be able to handle? It's really not any different than the roller coaster questions that you had no trouble with in Unit 2. Okay, it's just a different formula for potential energy. Okay, so as we were saying here, okay, if we're looking at something oscillating back and forth, okay, when it is at its maximum displacement, okay, V will equal 0, all of our energy will be potential. As we move this way, kinetic energy will increase, okay, and potential energy will decrease. Okay, when we get to equilibrium, we're moving at our maximum speed. Okay, our displacement is 0, so all of our energy is kinetic. But then as we move away and compress the spring, okay, the spring slows the mass down, but loads up with potential energy. So we see the potential energy increasing, okay, until we get to that point of maximum displacement this way. What did we call that? What was the special name for the maximum displacement of the object? Learned it yesterday. Starts with A. Amplitude. Good. I'm glad somebody remembered it. Okay. So that comes into play a little bit as well. Everybody with me so far? Yeah. So we do a couple of examples here and see how we do with those. All right. That one we're not going to do. Actually, that one either. Okay. So a spring has a spring constant of 30 newtons per meter. Okay, the spring is pulled 1.5 meters from equilibrium. We don't have the picture on there, but we can imagine. Okay, what's the restoring force? All right, so here's what they give me. K, and they give me X. Now, they don't tell me which direction it's pulled, okay? But since it says pulled, I'm going to assume that that's positive, okay? Because I'm pulling it away from equilibrium. If I was pushing it, I'd be pushing it to the left of equilibrium. I would consider that to be negative. Everybody all right with that? Okay. They didn't say one way or the other, so we just have to kind of go with it. Okay, so we're trying to find the restoring force. All right, so the restoring force can be calculated using whose law? Hooke's law, right? Because Hooke's law is what tells us the restoring force in a spring. So that'll be negative K times X. So all we do is take negative, okay, 30 times 1.5, and what we get is negative 45 newtons. All right, so in other words, the spring is pulling back towards equilibrium, that's why it's negative, with 45 newtons. Okay, I displaced it. I'm going to say that my 1.5 meters was a positive 1.5 meters, therefore the force is going to be negative. In this case, all you could write would be negative. Okay, this is actually a poor question because they should have said pulled to the left so that I could say 45 newtons to the right. That way, right for you, left for me. Yeah. Okay, everybody all right with that idea? Like I say, Hooke's law is not difficult. Here's the trick with Hooke's law. The trick with Hooke's law is determining when to use it. Because a Hooke's law question can sound a lot like a conservation of energy question. They're going to give you a lot of the same information. They're going to give you displacement. They're going to give you spring constant, okay, things like that. The difference is a Hooke's law question will generally only deal with one point in the movement. A law of conservation of energy question has to deal with how many? At least two. Okay, because we have to compare initial and final. Hooke's law only deals with the force at one spot. Okay, so that's one thing to look for when you're reading through a question. If the question's, just saying, here's a bunch of information, calculate the displacement at, when the force is this much. Okay, well, I was given force, something I'm not usually given in a conservation of energy question, and I was only asked about one position. Okay, conservation of energy question, probably not going to get force. Okay, and you're going to be given information about more than one position. All right, so it's just something you have to read the questions carefully. All right, I want you guys to try these two. They're pretty easy. Probably only take you a minute. Okay, give those two a try and then we'll talk about them. All right, so let's quickly have a look at these two. So if we want to determine the restoring force of a spring displaced 55 centimeters when the spring constant is 48 newtons per meter, we don't even have to manipulate. We just have to convert the centimeters to meters. Okay, so we'll have negative 48 times 0.55. That's a 5, okay, meters. All right, so we'll end up with negative 26.4 newtons for that one. It's in the opposite direction of the displacement. All right, for question number 2, it says a spring requires a force of 100 newtons to compress it, a displacement of 4 centimeters. All right, so we have X being 0.04 meters, and we have the restoring force being 100 newtons. Now, if that number is positive, this one has to be negative. They don't tell us that in the question. It's something we have to recognize. If we don't recognize that, we're going to get K to be a what? Well, I mean, it'll end up positive, but it'll be weird, okay? And it can end up that we don't want, like, K can't have a positive or negative value. K is an absolute value. All right. So what we have here, okay, is we'll have our 2.5 times 10 to the 3 newtons per meter. Okay, we'll calculate that simply by going force restoring equals negative K times X, and then I'll bring that negative over with me. So I'll have negative 100 divided by negative X, which would be negative 0.04. Okay, and that way I get a positive K. All right, and I've still reflected all the vector stuff that goes along with this, and that's going to be 2.5 times 10 to the 3 newtons per meter. Okay, questions on how that works? Okay, like I say, with Hooke's law, it's pretty straightforward. Most of the time for Hooke's law, it's going to be a question like what Hooke did, which is a hanging mass. Okay, meaning that you might get the mass of the object that's hanging from the spring, and you'll have to do what Hooke did and say that the restoring force is equal to the force of gravity, and then calculate from there. All right, that's very often how it works. Okay, I know that a couple of years ago, the question I put on the unit exam was about weighing fruit at the grocery store. Okay, if you put fruit in a scale, okay, it's the force of gravity that pulls on the spring in the scale that tells you its weight. Okay, so I just said you put this fruit in the scale, and it says it weighs this much. What's the spring constant of the spring if it was displaced this much? Okay, and people messed it up because they didn't understand what I was asking. Okay, I gave them the restoring force because I gave them the weight of the fruit. Okay, and they just didn't recognize that those two things had to be equal. All right, you guys follow me on that? Okay, so here's one like that, okay? A mass of 510 grams is attached to a spring that's hanging from the roof, okay? The spring stretches ½ a meter. What's the spring constant? Okay, so what they gave us here was the mass, which I right away want to convert to kilograms. And they gave me the distance, right? 0.500 meters. Now, I would say that that distance is down, right? If this is from the ceiling, it was stretched in a downward direction, okay? So we're looking for what's the spring constant. So the force is going to be calculated by going m times g, right? Because it's the force of gravity that's pulling on the spring. So I'm going to say force of gravity m times g equals negative k times x, right? And I'm going to have 0.510 times negative 9.81 equals negative k times x, okay? And so we just bring everything over here. Now this one ends up being a little weird. You're probably going to get a negative number for k even if you bring the negatives over, but that's fine, okay? Just understand that when you do calculate k, it is actually just an absolute value. I wouldn't mark it wrong if you wrote k was negative, but k is not negative. Right, so when we solve for k here, we're going to have 0.510 times 9.81, okay, divided by our displacement, which was 0.5 meters. I've just made it all positive because it's essentially all in the same direction, okay, and we're going to get k out of that. So whoops, that's not right. All right, so the spring constant's 10 newtons per meter, okay, on that one. Okay, so not a mathematically difficult question, but again, it's if you don't read it carefully and visualize the context, you won't know where to get the force from in order to calculate this, or the restoring force for that question. Okay. All right, that we're going to skip because we don't have to do multiple springs. And that one we're going to skip to because it's vertical. Okay, so this one here we're going to try together, question number 1. So I want you to just write question number 1 down, and then we're going to walk through it here. Yeah, write down question number 1. Okay, so in question number 1, essentially I've got a mass on a spring, but it's like on a table, a frictionless table. So it's oscillating back and forth horizontally. Okay, gravity is not a factor because it's on a table. We're told the table's frictionless, so friction's not a factor. What's the only force acting on that mass? What's the only force causing it to move back and forth? The restoring force, right? The force in the spring. So if the restoring force is the only force, then by default, it's also the net force. And that's how this question starts, right? Because it gives me, in this question, it gives me acceleration. We haven't dealt with acceleration in any questions so far in this unit, okay? But, okay, this one tells me the instantaneous acceleration is 4.11 meters per second squared left, all right? So the only force acting in this question is the force of the spring, okay? So it is by definition then the net force. So I'll have negative k times x equals, what's the formula for this? Mass times acceleration. All right, so now I can solve for the mass's displacement by bringing k over to this side. Okay, so now I can solve for x. So that's going to be 0.724, okay, times the acceleration, which is left, okay, so times 4.11, and I'm going to make left negative, okay, and then on the bottom I've got negative k, so divided by negative 8.21. So when I do this calculation, I'm going to end up with what kind of a number? Positive, because I'm dividing a negative by a negative. So I'm going to end up with a positive number. Since I made left negative, I'm going to end up with what direction for my x? To the right, which makes sense. Okay, if it's accelerating to the left, it has to be because it is to the right of equilibrium. The spring is pulling it the other way. Right? So the vector stuff here is important. Okay, so when we do that, we should get 0.362 meters to the right. Okay, we can just double check it. 0.724 times negative 4.11 divided by negative 8.21. Okay, 0.362. I would say right. Yeah, if it gives you left and right in the question, don't go to positive and negative in your answer. Use positive and negative for the math, but then go back to the direction. Same as we did in Unit 2. Okay. Now, question number 2, okay, another example here, slightly different, so we'll have a look at number 2 here. Okay, it tells me that I have a 50-gram mass. So I'm just going to write down my givens here. That's 0.050 kilograms. Okay, is attached to a spring that has a spring constant of 4 newtons per meter. Okay, the mass is oscillating with an amplitude of 1.12 meters. What does amplitude mean again? Maximum displacement. So A is really just an x value, right? It's the displacement. It just happens to be the biggest number that x can be. We want to find its maximum speed. So we're looking for v. What am I going to use to calculate this? Tanner? Okay, not work energy, but conservation. I want to use the law of conservation of energy here. At the maximum amplitude, what kind of energy does this mass have? Just potential. That's where the spring is most stretched or most compressed and the speed is 0. It wants me to compare that to the point where it has its maximum speed, which is where? Right at equilibrium, where it only has what kind of energy? Kinetic. Okay, so this is where that whole understanding part comes in. The math isn't hard, but we have to be able to visualize when it's at its maximum amplitude, it's not moving, all of its energy is potential. Okay, where does it have its maximum speed? At equilibrium, when all that energy is now kinetic. Okay, so really what we're setting up here is a conservation of energy question, okay, where we would say initial potential plus initial kinetic equals final potential plus final kinetic, but that's 0 and that's 0. Okay, initially it's at its maximum displacement, okay, and finally it's at its equilibrium position. Whoop, what did I do wrong? Yeah, I'm in such a habit of using that because I just worked on that with my Science 10s this morning. 1/2 kxi squared. Okay, all right, so we're trying to manipulate for the maximum speed. So what can I do with the halves right now? I can get rid of them because when I manipulate this for maximum speed, I'm going to go divide by half of m, right? The half's going to come over here. The half's going to cancel, right? So I'm going to have k times xi squared over m square rooted to get VF, all right? So we'll have the square root of KXI squared divided by M, right? So that's going to be, okay, 4 newtons per meter times 1.12 meters squared divided by 0.050 kilograms. Whoop, 0.05. Why does it not? Okay, so we're getting the maximum speed of that mass is 10 meters per second. Okay, so it's just law of conservation of energy. Okay, how did I know to use law of conservation of energy on that one and not Hooke's law? First off, it told me it was oscillating, and it asked about 2 different points, a maximum amplitude and a point where the maximum speed occurs. Those are 2 different places, so I knew it couldn't be a Hooke's law question from there. Okay, if it's a Hooke's law question, it's about 1 spot. They could give you acceleration. They'll talk about forces. Okay, but in a conservation of energy question, they're not going to talk about acceleration. They're not going to talk about forces unless it's a 2-step question. Okay. All right. Try this one. This is a 2-step question. You'll have to use some of the stuff we learned yesterday and some of the stuff we learned today. Okay, I'll give you a few minutes. It might take you a while. You have to think critically about this one. Okay, but I think you guys can handle it. So I'll give you a few minutes on that one. Okay, so let's have a look at this one. They want to know the period of oscillation of this mass on a spring. So one of the first things I need to do is look at what things do I need in order to get the period, right? Well, according to the formula we looked at yesterday, to get the period of a mass on a spring, I need the mass and the spring constant. Now they give me the spring constant in the question. They told me that K is 5.03 newtons per meter. Okay. Now they also tell me that the maximum amplitude is 0.1225 meters. And they tell me that the maximum speed is 5.13 meters per second. All right, so they've given me information about 2 places in the oscillation. So if I got information about 2 different places, I should start out with what? Conservation of energy. Now, when I look at conservation of energy, okay, that's going to say EI equals EF. We're dealing with maximum amplitude for one of these, so that's going to be 1/2 KX or KA squared equals 1/2 MV squared. Okay, I've got K, I've got X, I've got V. Can this help me get mass? Yeah, because I have everything except mass. Once I have mass, then I can go back to the period formula and finish it because I have the thing I'm missing. All right, so it's a 2-step problem. And very often you run into 2-step problems when it comes to simple harmonic motion. All right, so we're manipulating for M here. So we would divide both sides by 1/2 of V squared. So the halves will cancel. Okay, so I have kx squared over v squared equals m. So that'll be 5.03 times 0.1225 squared divided by 5.13 squared. Okay, so there's the mass. Is it pretty small? Yeah, it's like 2.8, 2.9 grams. Okay, it's really, really small. All right, but that's the mass that I've got on this spring. Now that I have the mass, now I can plug in and calculate period. All right, so I'll have T equals 2 pi times the square root of that 0.0028 whatever, okay, divided by 5.03, right? Yeah. Okay, so we'll have 2 times pi times the square root of our answer divided by 5.03. All right, so we got 0.15 seconds for the period. Right. This is a very small mass on a relatively heavy string or spring, so it's not going to take very long for it to oscillate back and forth very much. Okay, questions on that? All right, once we realized those were the steps we had to do, was there any tough math? No, again, it's not the math here, guys. It's just like Unit 2. It's not the math that's hard. It's visualizing what things do I need to do to get there. All right, I want you guys to try number 1. We'll leave it at number 1. We won't do any more than that today.